Data analytics is the foundation of AI. Without understanding data, you can't understand or trust the intelligence built on it. This video course is introductory to data analytics for the age of AI. Created by Dr. K. Seefeld. The material used in these videos is in the Text Data Rookie's Introduction to Data Analytics. Available as a free PDF from the website www.dataanalyticscurriculum.com. Chapter 3, Statistical Concepts. Welcome to Chapter 3 Section 2, Probability and Distributions. Learning Outcomes. In this lesson, we'll explore how probability is used in machine learning and how to apply Bayes' theorem to make informed predictions. By the end, you'll understand the role of probability in models, see how data distributions affect assumptions, and learn to update predictions when new evidence appears. Probability in machine learning. Probability is a way to estimate the likelihood of different outcomes. In machine learning, it's essential for predicting results, evaluating models, and making decisions under uncertainty. Many models, from spam filters to recommendation systems, rely on probabilities rather than certainties to handle real-world complexity. For example, a model might predict there's a 70% chance a customer will buy a product next week, not just a yes or no. Normal distribution. The normal distribution is a symmetrical, bell-shaped curve centered at the mean. Most values cluster near the average, with fewer at the extremes. You see this pattern in many natural datasets, like heights, test scores, or measurement errors. It's also an important assumption for models such as linear regression, because normally distributed errors make predictions more reliable. Why normal distribution matters. Assuming a normal distribution helps ensure the reliability of statistical tests, confidence intervals, and predictive models. When data are roughly bell-shaped, we can make more accurate inferences and predictions. For example, understanding that most patients' blood pressures fall near an average allows healthcare models to flag unusual readings effectively. Bernoulli distribution. The Bernoulli distribution models binary outcomes, situations with only two possibilities, like yes/no, 1 to 0, or success/failure. It forms the foundation for binary classification tasks, which are common in machine learning. For instance, deciding whether a customer will churn or stay, whether a patient has a disease or not, or whether a transaction is fraudulent. Use in machine learning. Bernoulli distributions let models assign probabilities to these two-class outcomes. For example, will a customer make a purchase, 1, or not, 0? Or, is a transaction fraudulent, 1, or legitimate, 0? This simple concept underlies many practical applications, from e-commerce recommendation engines to fraud detection systems in finance. Bayes' theorem. Bayes' theorem provides a method for updating the probability of a hypothesis based on new evidence. It's used in naive Bayes classifiers, Bayesian networks, and other probabilistic models. This theorem is especially helpful when dealing with uncertainty, or when data are incomplete or constantly changing. Bayes' theorem in practice. Let's say we want to predict whether an email is spam based on keywords like free or win. Bayes' theorem combines prior knowledge, like the overall spam rate, with new evidence from the email itself. This allows the model to adjust predictions as more data are observed. Similarly, medical diagnosis models can update the probability of a disease when new test results become available, improving accuracy over time. Bayes' theorem formula. The formula is P(He) equals P(Eh) times P(H)/Pe. Here, P(He) is the probability of the hypothesis given the evidence. P(Eh) is the likelihood of seeing the evidence if the hypothesis is true. P(H) is the prior probability of the hypothesis, and Pe is the overall probability of the evidence. This framework lets models combine prior information with new data in a principled way. Bayes' example result. For example, the probability that an email containing the word free is spam might be about 23.3%. This demonstrates how base rates, or prior probabilities, influence the final prediction. By continuously updating predictions as more evidence comes in, Bayesian models adapt and improve over time, whether for emails, customer behavior, or medical diagnoses. Closing summary. In summary, probability and distributions are central to machine learning. From normal distributions that guide assumptions in regression models, to Bernoulli distributions for binary outcomes, these concepts help us understand and model uncertainty. Bayes' theorem adds the ability to update predictions dynamically as new information arrives, making our models smarter, more flexible, and better suited to real-world data.